So you may have been taking notes, but for this section, this is definitely notes. And you may not understand everything in this section, but I want you to write it down so that we have a common base of knowledge together. Okay, so I'll make a box. It goes like this: arithmetic, geometric. Metric. This is a table. Not a super table. Kind of a super table, but it's not a table of values. It's probably it's going to be an organizational table. Okay. And how it's going to be organized is we's going to say recursive, because we've learned four things. We've learned arithmetic sequences, we're learning geometric sequences, and we're using recursive functions and explicit functions. These things all overlap. Well, not overlap. I think you get what I'm trying to say. Alright. Arithmetic recursive. I'll just write an example. F of n. And anytime you see that, that's a powerful statement. That means any value in the sequence, any amount that is created by a situation, any amount of push-ups that that dude does. Here's the amount. The input is the day he did it on. But the amount of push-ups is the function value with that day as an input. I will continue with his example. Recursively, that means it's going to be another function value. Which function value? The one that's right before the nth value, n minus 1th value. And the rule is he did 2 more each day. He did 2 more each day. You also need a starting place. So the function value for the first day was 3. Let's look at a geometric thing. We'll do the growing dots. The number of dots, the one that really was growing a lot, where there's a lot of dots, started off as 3 and then grew from there by doubling. So this will look like f of n. Any number of dots with an input n is equal to f of n minus 1, the number of dots that were there right before, time is doubling, so it's times 2. Not just 2 more, but double it. And then this one actually had a 0th term at the beginning. Before the first minute was up, there were 3 dots there. Okay, so that's our recursive function for an arithmetic sequence and a recursive function for a geometric sequence. What about explicit functions? Explicit functions can operate all on their own with only one piece, not 2 pieces of information. And how you build it is, as we learned with Scott's push-ups, the function value is equal to the number he did on the first day plus the common difference, the new ones every day. And then you have to multiply by how many times he's done 2 extra. 2 more, and 2 more, and 2 more. How many? Not n times, but n minus 1 times, because he didn't do 2 extra on the first day. He just started with 3. So because 3 was the first day, we don't need a 2 for that day. And indeed, if you put a 1 in here, that turns this into a 0, and 0 times 2 is 0. That means no extra when you put in a 1. On the first day, no extra. And then after that, there is extra. On the second day, 1, because 2 minus 1 is 1. 1 extra. On the third day, 2 extra. On the fourth day, 3. On the fifth day, 4. It's our little adjuster. And that's done. That's the whole explicit function. It has where it starts and how it grows and how many times you need to grow it. Let's just find out how many push-ups you would do on day 100. This is an example. When n equals 100, f of 100 equals 3 plus 2. Oh, we replaced the n with 100. That means we replaced this n with 100. F of 100 equals 3 plus... Order of operations, what do I do first? Inside the parentheses. Okay, order of operations, what do I do next? Multiplication. So 2 times 99 is 198.
Attention teachers, if you have not done so already, please come to the main office staff room and pick up your handbook to be distributed during third period. Thank you.
Whoops. Okay, he does 201 push-ups on that day. My next class is about to start, so I will finish this video in a minute.